because my brother was doing his medical training at the time. Otherwise, I had admissions in other schools too. And I ended up in North Carolina. It worked very well for me, thank God. But at NC State, North Carolina State at Raleigh, basically I did both my master's and PhD in materials engineering with a minor in mechanical. And then in 1975, Oregon Graduate Institute, which now is part of OHSU, some of it is part of PSU. They hired me to run their electron microscopy lab, and I did that for 4 years, 1975 through 79. And in 79, these folks made the mistake of hiring me. But they have been stuck with me for 37 years. It's been wonderful 36 years. I've done pretty much everything, teaching, administration. I was assistant dean, associate dean, stepped down from all that. Now I'm doing full-time teaching and just loving it, basically loving it. Okay. Now, some of you know what this is, old-timers, right? This is how I did my undergraduate work. Slide rule, right? Okay. My first calculator was in this country graduate school, and that was Texas Instrument, and they didn't call it TI. I still have it in my office if you want to look at it. It's called SR50. Guess what SR stands for? Slide rule 50. Maybe there was something to be said about that. At least we had some respect for numbers, and we had some feel for numbers, okay? Because you had to figure out where the decimal point is, right? If the answer is 5,000 or 5 million. That's not happening anymore, unfortunately. Just last spring, I was sitting through our senior design presentation. I was teaching that class. And one group, because they've got these fancy finite element modeling programs, solid modeling program on the computer, which gives beautiful pictures, and they were giving me stress values like 25 million psi and 2 billion psi. And I said, aren't you embarrassed to even mention those numbers? So basically a respect or a feel for numbers has sort of gone away because of all this. Anyway, so this is what is happening to my life. This is called upgrade. I was a typewriter man or woman here. The typewriter is taken away. Computer shows up. The lady is happy. But then the lady is gone. In fact, I'm waiting for that time myself. I want to retire in about a year or two myself. I want to be upgraded there. Okay. While I'm getting upgraded, my students are doing this, and you all know what I mean. They're totally connected to technology, right? I have a grandniece staying with us who got her bachelor's degree from Pakistan, master's from UW. She is really connected to her iPhone. You know, she cannot even move without it. You know, she has to bring it to dinner. She'll take it to this restroom, and basically, that's what is happening. No problem. I'm ready to retire. Okay. We'll start from ab initio, really very basic stuff. And I realize many of you are, you know, welding inspectors, CWI, and you know, people like Neil are working in testing labs. So this is very basic stuff. We'll go through basic stuff fast. Please stop me because I don't want a monologue. If there's any question, and there's no such thing as a stupid question in my mind. These are all genuine questions. So ask me any question if you want. But we'll go through some definitions, some type of loading and whatnot, and then go from there. Should I turn the lights off so that you can actually see it?
I don't really have a problem.
Well, let me turn these lights off. Let's see. If I were to turn, the problem is all or nothing. Is that too dark?
That's fine.
Fine? at least you can see what's going on. So my idea is to go through these things pretty fast, and if there is any question on these things, then we can talk about that. But most of it should be kind of familiar to you because you come from welding background, testing background, and so on and so forth. Stress and strain are the two main things that we define in mechanical testing. Normally you will take a STM standard tensile bar, and I'm sure you have all seen these things, aluminum, steel, what have you. This is STM standard steel bar, aluminum bar, 0.505 diameter. You put it in a testing machine and pull it, and basically fracture. Okay. So stress, force divided by area of cross section. Strain is the change in length divided by original length. In metals, thank God, things don't move a whole lot. They move very little, and I'll show you how you can actually measure it. Okay. So the change in length is in terms of micro inches, 10 to the minus 6 type thing, and the original length might be 2 inches, 1 inch gauge length. In this case, the gauge length would be 2 inches, so we'll put an extensometer on it to start with 2 inches. And so forth. Okay. Now, yield strength, I'll show it to you on a graph in a minute. Tensile strength and modulus velocity, these are standard things that you actually have to have in order to do some design work, right? So, yield strength is when the material starts going from elastic, when it's behaving like a rubber band, goes back to, you take the load off, it goes back to original dimensions. It goes beyond that and it goes into permanent deformation. Tensile strength is the highest point on the stress strain diagram, which we'll show you in a minute. And the modulus of elasticity, a lot of people don't have the right idea about this. They think that this thing is kind of changing all the time. No. In fact, modulus velocity is like the fingerprint of a material. It's a material constant, does not change. You take pure iron, which is soft, you can cut it with a knife, and you take ultra high strength steel that they make landing gears out of, modulus of velocity is still the same, 29 million psi, or 30 million psi for steel, for example. So that's a very important point to keep in mind, that modulus does not change. What we do change with heat treatment and whatnot is the strength. Okay. Now there are many different kinds of loadings, and of course we can't go into everything. But tensile load, which is trying to stretch things, compression load, which is trying to squish things, and you can have short section. Normally you take short samples. There's a reason for it. I'll show you some sketches in a minute. Or a long section, bending, torsion, shear. These are different kinds of loads, and I'll show you some sketches in a minute. Most of the loading on a weldment can be categorized under one of these. In many cases, combinations of these loadings occurs. That's the bugaboo. You don't get simple tension or simple compression. A lot of times it could be tension and bending or something like that, no combination. Also, these loading may be applied in a dynamic mode, impact. You hit with an impact, there's a pulse which actually dampens like this. It's a form of fatigue. And then fatigue, which is cyclic loading, load, unload, load, unload, load, unload. If you look at the literature on fatigue, they'll say anywhere between 50 to 90% of the fractures in the real world occur due to fatigue. So if you took even 50%, 1 out of 2 fractures are due to fatigue. It's everywhere. Anywhere from your human body, while you're walking, you are loading and unloading, to offshore drilling rigs, with wave motion, to airplanes, to trucks, to automobiles, and that's the reason that all these companies will be doing a lot of fatigue testing, on real world things. In fact, I just got the Advanced Materials and Processes magazine. I don't know, some of you probably get it if you're a member of ASM. And the very latest issue, on the title page, it says, mechanical testing goes big. And they've got a testing machine. The guy is actually standing on the machine bed, okay? And the crossheads are really huge, and you can actually do real world testing of beams and column connection and whatnot, basically. Not little bitty sample like these, for teaching purposes. So basically this is what we are saying, that This is how we define stress, E over A force, and the A will be this area of cross section, basically. Okay. So that's where the normal stress is occurring, essentially. And when I'm doing that, it's elongating, and it's actually due to Poisson effect, it's actually shrinking in the diameter. So the strain is L minus L naught over L naught. So you start from L naught, which is like 2 inches gauge length in case of these samples, and then you stretch it beyond 2 inches, right? Whatever, 2.3 and so forth. That's my strain. Okay. And these things can be measured very accurately with some of these things which I'll show you. All right, so essentially then this is my tensile test machine. And we do have a tensile tester, compression tester downstairs if you want to look at it, if you have not done that before. And we also have a fatigue tester downstairs, small fatigue tester. We got rid of that big MTS machine, Neil. We actually donated it to Bill Wood's operation. It's at Portland State now.
I think we may have seen it a few months ago when we were down there.
It was a fantastic machine, right? It was a fantastic machine. Control systems were kind of old, and it got used like every other year, so we were not using it much. We got a smaller machine for biomedical type testing, because one of our faculty is in biomedical stuff. So here they are showing a 3-point bend test. And normally this bend test is used for brittle materials, for ceramics and powder metals and whatnot. Because as you can imagine, if I were to take a brittle material and put in that grip here and here, it's going to go crunch. Okay, so it doesn't work, basically. In other words, you actually use 3-point bend for brittle materials and simple tensile testing for ductile materials. This is my stress strain diagram. Basically, after you've done some tensile testing, you plot stress on the y-axis and strain on the x-axis, and typically this is the kind of curve you'll get from a piece of steel or aluminum or what have you. And y here tells the yield strength. That's where it starts going from a straight line into a non-straight, so from an elastic regime to a plastic regime. And of course, ultimate tensile strength is right there, the highest point. Yield strength, ultimate tensile strength, and then of course eventually fracture. Now, we were talking about modulus of elasticity. That's basically the slope of this line. And that slope, as I told you, doesn't change. That comes as a surprise to my students, that you take soft iron and this will give you 30 million psi, and ultra high strength steel, 200,000 psi tensile strength, give the same modulus. Yes, because the modulus of elasticity is really a measure of the bond strength, the strength of the atomic bond. Unless you change that strength of the atomic bond by heavily alloying things, that doesn't change. Okay, please holler if you have any questions or any comments. Okay, I don't want it to be a monologue, as I say. Normally, compression testing is normally not done on ductile materials unless you are doing manufacturing research, because most of the manufacturing processes use compression, right? Whether it's forging or rolling or something like that. I don't know how much compression testing you do, Neil.
Not with steel, concrete. A lot of
Concrete, certainly. Yeah, brittle materials, yes. Because it turns out that with ductile materials like metals, the behavior in tension versus compression is about the same, because they actually yield and fail where there is maximum shear. So kind of like a mirror image in tension versus compression. Not so with brittle materials like concrete. Concrete may fail at 3,000 psi, pounds per square inch. In tension, it might take 30,000 psi in compression. Okay, so they are totally different. Okay, and actually there are some tricks that people do to make them stronger in tension, And one of them is, of course, pre-stressing the concrete, right? And they do that on glass too. And if you suffer through this 1 hour presentation, I might actually show you a neat video or two what they have done with glass.
Actually, the biggest trick with concrete, of course, is to make it a composite material and put steel in it.
Right.
So the steel is operating in tension,
Correct.
and the concrete's operating in compression.
Correct. In fact, they have put fibers. I teach a full class in composite materials, fiber reinforced composites and whatnot. And they have put fibers into concrete. They have put, air entrained concrete. It's mind-boggling what they're doing with concrete. Concrete that will float, concrete that can bend like this, and so forth. So they are doing some funny things with that. Anyway, compression is normally not used, but it is used a lot in manufacturing research. There's a thing called Concurrent Technology Corporation, the Navy Metalworking Center, right, in Johnstown, Pennsylvania. And they do some fantastic manufacturing research for the Department of Navy, which actually trickles down into commercial area, and then universities are involved. And I've been there a couple of times. They do a lot of computer modeling, analytical stuff, and experimental stuff, and see how they all match. They do a lot of this. Now, of course, if the sample was too long, and you do compression on a tensile bar like this, it's going to buckle on you. And that's why you normally don't use long samples for compression. Only short, stocky samples. 3-point bend, I've already shown you that. In a way, you are actually testing the material in tension, because you start loading it there. 3-point bend, okay, 2 supports and load there. Compression there, tension there. Normally the fracture will start here, okay, on the tension side. Ceramics will break in tension first. 99.9% of the time it starts here. You can have torsion on a shaft or whatever. And torsion is actually, you can think of it as shear. So I take an element and this is shear. Well, the difference is normal, let's see. I've got this tensile bar, I hope you can all see it. And I put load on it. This plane will see normal stress. It's trying to separate, right? Normal stress trying to separate. Shear stress is trying to basically smear things, okay? And it turns out that if I do simple tensile test, normal stress on this plane and maximum shear is at 45 degrees to it. So more often than not, you will see a very peculiar fracture, which is called a cup and cone fracture. You can take a look at it later, where you'll get a cup on one side and a cone on the other side fitting together, and it will have a 45-degree wall. Okay, basically, it's a classic ductile fracture in material. All right, but so you can look at torsion as either a shear or actually a combination of a tension here and a compression there. Okay, and that's the reason that if you were to take a brittle material, you will actually get a very fancy 45-degree fracture, because this is where chalk is brittle, right? It's going to fracture where there's tension. Okay, so it's going to fracture along that line. Okay. And that's a pretty interesting demo for students. All right. Now you can also have shear like that. If you got a lap joint or something like that, then you'll have shear. Now in real situations, these are some real things: torsion loading. You have a shaft and you have welded together here, and of course you're putting a force there. Some simple formulas for shear stress and so forth. You can have another shear loading like this, for example, T-joint, stuff like that. Please stop me or make a comment or make a question so people don't go to sleep. Actually, I don't mind if you go to sleep, because I see that all the time in my class. Half of the students are playing with their iPhone, the other half are dozing off. Okay. I find that pretty interesting. So, fillet weld, you're all familiar with fillet weld, of course, and you can have, shear loading here, transfer shear, longitudinal shear, if you're applying load there. Okay. Now, there's a concept of stress concentration, and I'll show it to you visually, okay, eventually. You have a bar, and you can actually calculate the stress here, no problem, if you know the stress, if you know the area, sorry. But if you were to go and put a notch or a hole in there, the stress level just shoots up, depending on how sharp that notch is. People have calculated these things. I take a plate, and I put a tensile load on it, very easy. I figure out the area, and I can figure it out. If I put a hole in there, the stress has gone up by a factor of 3. It's no longer, force over area, it's 3 times. I put a notch here, factor of 10, stuff like that. So stress concentration is a big bugaboo, and I'll show it to you visually eventually. Big thing, stress concentration. Now, you may have impact loading, okay, which is the worst. Which is the worst thing. Because what you're doing here is actually the strain rate. The rate at which you are loading is very, very high. It's no longer very slow pulling. Okay? It turns out that ductile material like aluminum and steel that you pull slowly may behave like a piece of taffy. But if I were to do this, very high strain rate, load rate, it's going to fracture in a brittle manner. Now think about it. People who are doing manufacturing research, a lot of these manufacturing operations like forging, I mean, you have all seen forging, hopefully. You're going bang, 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 right? Very, very high strain rate. So you need to do that. And that's why people like at this Johnstown, Pennsylvania facility, Navy Metalworking Center, they've got machines which can do that kind of testing. Okay, you take a slug, and rather than slow squishing it, you can actually do that, high strain rate. Now, impact testing, in fact, that reminds me of a story. Way back when I was going through graduate school in Raleigh, my minor was in mechanical, so we would take classes in mechanical and aerospace engineering department. And downstairs they had a lab where they were actually testing materials, would you believe, with a gas gun. Bang! You'd hear that bang, and there was a target, and you're hitting it with that gas gun, basically a projectile, because you want to see how materials behave with high strain rates. Anyway, Sharpie impact test. Again, most of you may be familiar with it. These samples are here for you to look at the end of the presentation. Sharpie bars are basically, you can see the geometry there. It's like a 1 centimeter cross section, and then about, 5 centimeters, I don't remember, 5, 6, 7 centimeters long. And basically, there's an impact load that hits it right there, behind the notch. So it's trying to open it up. And this actually gives you a different property. This actually gives you what we call toughness, impact toughness. I find that even in textbooks they make mistake. They call it impact strength. It is not strength, it is impact toughness. So what is the difference? Toughness is energy absorbed, elastic deformation and plastic deformation, and then fracture. So, when I say strength, obviously I mean y-axis. Yield strength, tensile strength, right? When I say toughness, I mean the area under the whole curve. Okay, this area. This is really the work done in order to deform it. In physics, we define work as force times distance, right? So this is nothing but force, which I have normalized by dividing it by area. And this is nothing but distance that I am stretching. So this is really the work done, total work done, energy. In other words, it's possible to have a material with a low yield strength, but which stretches a lot to have a lot of toughness, right? It will be weaker but tougher. Are you with me on that? It will be weaker, strength will be lower, but can take a lot of stretching and toughness. In fact, Japanese have developed very low yield strength steels for such applications in earthquake resistant structures. So the structure with basically these beams and so forth will mangle and take all the energy. It's just like a crumple zone, right, in your cars, basically. So toughness is a different property. It's really the work or energy. Area under the stress strain diagram, essentially. Again, if there is any question, please holler. Or comments. Doesn't have to be a question.
I got a question.
Yes.
You mentioned if you cut a hole in this material,
Yes, sir.
it's 3 times the factor now, right?
Right.
So if on high carbon frames, if they build lightning holes or make the material lighter, they say stronger, how is that working?
Sorry, I had bad ear, so I could not get the whole question.
Okay. In frames, with trucks and different things like this, they put in holes where they've got, elongated sections in to lighten it up. But how's that giving it strength when you're talking about 3 times
Very good
factor
question.
for each hole?
Yeah, excellent question. Actually, you can take material off where the loading may be lower, and I'll show you that visually actually, photoelasticity. Photoelasticity is a fascinating technique, has been around for 80, 90 years, which is done for design optimization. So there are areas in the structure where you could take the material out and not do as much damage as you could do in some other critical areas. Very good question.
Well, and I was taught the word of ductility in relationship to what you're saying for some of these other things too. The plasticity, things like that.
And you would rather have, in fact, as far as I'm concerned, I tell it to my students, I would rather have a tough material. I don't care about strength, I don't know about this and that. Toughness is really critical. Aerospace industry is like 10 miles ahead of everybody else in terms of design and material and so forth. And they have developed the whole field of fracture mechanics, and which actually is toughness material. What they call damage tolerant design. We know that all materials have defects in them. Can you design something which will actually be able to tolerate those defects and still perform? Well, it turned out that we're not going into all the details of crystal structures and this and that, but it turns out that some materials show a big, huge transition in their toughness as the temperature goes down, and I'll show you a very dramatic effect of that. Some of you probably know that. What happened to ships in World War II, basically. But VCC metals, which means iron and steel and stuff like that, will go through a transition. You go a very low temperature, and the material which was taking so much energy to break now breaks like a piece of glass. FCC, like aluminum, we actually do this test here in our sophomore level materials lab. We test things down to liquid nitrogen temperature. Liquid nitrogen is minus 196 centigrade, minus 320 Fahrenheit. So really cold. Okay? And FCC metals, like aluminum, they keep their toughness even at low temperature. Wonderful materials. And this has to do with crystal structures, really. Body centered cubic or face centered cubic, stuff like that. Okay, types of notches. You can create notches just by poor design. Workmanship. Of course, you are in the real world doing this thing, welding and stuff like that. Of course, I assume that all of you are doing wonderful, excellent level of work. You know what you're doing. But workmanship, if it's poor workmanship, you can actually create mechanical notches, cracks, and undercut, this and that. And then there are so-called metallurgical notches. What do they? These are not that obvious. Mechanical notches are easy to see. These you can't see sometimes. Abrupt change in strength levels, mismatch of base and weld metal. Arc strikes. Struck an arc there. There's a martensitic structure there. Crack has already started. Weld spatter. Spatter ends up somewhere, basically very high, fast rate of heating and cooling. Hopefully, you didn't get martensite, but on steel, you might. And last but not the least, residual stresses. Those are really bad because you don't see them. You don't think that the structure is being loaded, and it's not, but it's got packed in stresses. Stress present in the material in the absence of applied forces. I don't see any applied forces. Nobody is loading it, and it still has got some stress packed in it. And I'll show you some of that with photoelasticity. Stress concentration we already talked about. The stress gets concentrated at discontinuities to a level much higher than nominal stress. That too can be shown very easily with photoelasticity, and I'll show you that. Now, this is a very typical pattern of residual stress in weldments. It turns out that we hardly touch upon this topic in our strength of materials classes because there ain't no formulas. You can't calculate residual stresses. Basically, you measure it. You measure it by 3, 4, 5 different techniques, X-ray diffraction and blind hole drilling, and I've got a sample which I'll show you after we are done. You measure these things. Now, some very, very smart people are trying to do computer modeling because now computers have become so powerful. In fact, as we speak, somebody at Portland State, you know Lemmy, right? Lemmy Nikisho?
Yes.
Yeah. He's a faculty member at Portland State in mechanical. His area is computer modeling, and I'm more on the experimental side because I'm not smart enough to be a theoretician. So I do experimental stuff, measuring it. We are working with Boeing Portland on some residual stress analysis type research project. Hopefully, it's just getting off the ground now. Anyway, in environment, if you were to do an analysis of how the stresses are along the weld axis, if you were to measure it, you find that there's a very heavy amount of tension right there. And since the internal stresses have to balance, because if they don't balance in a body, the body is going to warp. So they have to balance. In other words, you got tension here, there has to be compression somewhere else. So this is compression. This is compression. Now, how high is that? I actually, last spring when I was teaching materials lab, we talked about residual stresses, and then I asked the students, what do you think? Let's do it as an auction. What do you think as a percentage of yield strength this stress level might be? And someone goes, well, maybe 20%. And I said, do I hear a 30? Do I hear a 40? And when we get up to 80%, I say, sold. Because really it can be as high as 80% of the yield strength. Think about it. The material is going to yield at 40,000 psi, and you weld it and don't do any other process on it to minimize those stresses. It might be sitting there like a taut spring, 32,000 psi in it, ready to go bang, okay? A lot of stress. In fact,
On your picture there,
Is it insinuating that the weld was done from the center out?
No. I don't know. I don't think. The idea here is that this is a line which is showing above is positive stress and below is negative stress, right? Tension, air, and compression. So no, I don't think it was meant that you are going this way and that way. I don't know what it could be. I'm not sure.
So just any weld
Anywhere, pretty much any weld.
in
pretty
any
much
direction?
anywhere, right? Any direction. Especially if you are, clamping it so it doesn't move and so forth. It may not be that high, it may not be 80%, it may be 50%, but there is residual stress left in it. And it can actually manifest itself in what they call stress corrosion cracking, a real world problem in things like nuclear power plants, where you're doing welding and you have to make sure that everything is okay. If you take a weldment like that and just leave it in air, moist air or water, there's a lot of water in our air in Oregon. This is what happens. Look at these cracks. And of course, they use dye-penetrant, so you can see the cracks. And of course, tensile stress is this way, so the cracks are opening, as you can see. Okay. This was residual stress, not applied stress, leftover stress.
You call that hydrogen cracking?
It could be hydrogen cracking, but this one is not hydrogen cracking, it's just corroding because there is stress and it's trying to open up and the water is getting in there, moisture is getting in there, just corroding it and the cracks are opening up. Hydrogen embrittlement is a huge problem. In fact, it's such a huge problem that I spent 3 years of my life working on it. My master's degree was on hydrogen embrittlement of nickel-based alloys. It turns out that hydrogen, being the smallest atom, atomic number 1, is like the Curious George, it gets into everything. Aluminum, steel, whatever, titanium, it will make them brittle. So it's a big thing, but that's a very specialized form of stress corrosion cracking, if you may. All right, let me just zip through these because we have until 8 or something like that. 1 hour, right?
Hour and a half, I mean, whatever.
No, I don't want to keep
Right.
going. Basically, I'll just zip through these and then show you some stuff there.
If it gets to 9 o'clock, we'll start walking out.
No, I can't even survive until 9. My voice. All right, so basically shrinkage stresses, that's what you're dealing with. Distortion, butt joint, for example, okay, stuff like that. So this is all residual stresses. Now, keep in mind, you're dealing with steel, you're heating things up, it's cooling down, so thermal stresses, plus it is transforming, right, from ferrite to austenite to, again, delta ferrite to liquid and then coming back. So all these transformations also put stresses on it because the crystal structures are different. One is more close packed, one is open. It's actually heating. It's alive, so to speak. Okay, again, longitudinal and then T-joint. These are from different books, so I don't think it's something special about it. You can get these from any books on welding. I use Howard Carey's book, fantastic book on welding, from very first edition, now it's up to 6th edition or 7th edition. I've used it for 30 years. Very good book on welding and stuff. All right, so this is the idea of stress concentration we're talking about here. A hole there, and of course if you put a hole in there, in fact there's a simple numerical formula as well. What they are telling here is the severity factor as the radius of this hole goes down, the stress intensity factor goes up. You already know that. I already told you this. The sharper the notch, the more the stress intensity.
Khalid, a couple of questions for you.
Sure.
obviously in the welding business, one of the things that we're doing, besides joining the materials, is introducing a tremendous amount of stresses. The most common method of stress relief is heating and cooling, transforming the materials and removing some of the stresses.
Right.
There's also, and it's been popular in past years, and I'm just curious on your experience, of vibratory stress relief, mechanical relief of stress versus heat. And I've kind of seen it as a voodoo stress relief, but I'm interested in your comments on that.
Funny that you mention it, because while I was at OGI, we were involved in a project. In fact, we had a paper or two on that, vibratory stress relief, VSR. You may think that it's voodoo, and it may be voodoo, but I think there is something to it. Because what is happening, the idea is that as you are welding, or even after welding, you can actually vibrate. And I think what is happening is there's some micro plasticity going on, micro yielding going on, which is bringing the stress level slightly down. It's not going down to zero or anything like that. There's some microplasticity going on because of all this. So yeah, it's voodoo science. In fact, residual stress analysis is also voodoo science. Although what you see there is a standard ASTM technique now for measuring residual stresses, but a lot of it is black art right now. You had a question there.
Could it also be linked to the phase change between the FCC and BCC?
Yes.
The same material changing between them and having vibratory stress relief during that transition?
Well,
I think you'd have to induce heat for that to happen.
yeah, I'm not
The welding heat.
sure, right. Actually, the crystal structures change because of heat, temperature, right? Yeah, there is a certain temperature at which it will go from BCC to FCC and back.
Right.
But this vibratory stress relief, remember Leonard Thompson, there was a fellow, right? I don't know if he's still around or not, but he was kind of an expert in that field, and he would apply it during welding as well as after welding, but during welding. And he would swear by it.
That's the way we always did it, was actually during the welding process.
And some of our common
And,
works.
and are you doing it right now?
I used to do stress relief for a living, now I do CWI.
Huh?
But when I did stress relief, we did vibratory, we did it during the welding process
Right.
and removed the preheats and everything. We just did vibratory.
Wow.
And it relieved the stress. They had all sorts of qualified WPSs to prove
Wow.
that it worked. And, you know, I'm
And
not an
again-
engineer,
again, my
I can't tell
take
you
on
what
that-
exactly it was doing, but.
Yeah, my
it
take
worked.
on that would be really some microplasticity going on, which is like, you got residual stress in something. If you stretch it and let go, you've actually brought the stress level down. Okay, that's called proof stressing. Yes.
Okay, so this goes back to whether you use flame heat or induction heating then. As to whether you're gonna do vibratory heat or stress relief.
I don't think it's
The other
heating
one.
it up. If you were to do, for example, VSR, vibratory stress relief has been used during welding, as well as I've heard of after welding. So it's not necessarily heating the material due to vibration, but what is happening is things are moving relative to each other, which means some kind of plasticity happening in there, microplasticity. That's my take on it. Conjecture.
Would that affect the fatigue properties then?
Probably fatigue properties would be better because now you have less residual stress. Just a guess. Just probably. So let's get back to this business of stress concentration in the welding business, since you're all in the welding business. This is from Kerry's book. It's really a very good visual because it shows you what can happen. A regular butt joint with groove weld, no problem. Think of stress as a fluid flow, water flow. Okay, water flow. The flow pattern is a good way of visualizing things. And it shows me that static tensile strength, 100%. Resistance to fatigue, 100%. Impact strength, 100%. In other words, things have not been affected here. Now, this will be double double V, right? Okay, but, and there's a little hole left in there. That is the bugaboo, right? Static tensor strength has gone down by 15%, 85. Resistance to fatigue, 35%, 1/3. Okay? Impact strength or toughness actually has gone down by 20%. Again, another notch here, if you leave a notch in there, 70, 15, fatigue. When it comes to notches, fatigue will actually show you what you have done wrong. You don't want any notches where there's fatigue involved, fatigue loading. And again, this one is probably the worst. You can see there's a big, huge discontinuity. This is 60% of static tensor strength, 40% loss. This is 90% loss. And this is 60% loss in tight toughness. Okay. So the point is, discontinuities are bad. And I think you already knew that, because you all come from welding background. This is in a T-joint stress pattern, similar story. But here, again, we are trying to show a stress pattern, and there's a symmetric arrangement, then you may be okay. But if it's an asymmetric like this is the most terrible design. As you can see, this is only 30%. This is just 10% of what was. And this is 10%. So this is the worst case scenario. Stress concentration. Now, I don't have, I have a number of these other things like defects and so forth, but I will skip those because you all know what welding defects look like. You've dealt with them. But those welding defects can do some interesting things. These are on the micro level, but they can do things on the macro level, right? Does anyone recognize this ship? USS Schenectady. In fact, I think it happened right here in Portland.
Yeah.
Some of you may or may not know this, but Portland was churning out, Port of Portland was churning out a ship a day during World War II. And there were dozens of these ships which broke in half, I think a couple of dozen, which broke in half and in thirds, sitting right there in cold water. And people didn't know what was going on. Of course, welding procedures were not that refined at that time, but the cold waters did the trick. And this is when we figured out what was going on with this ductile to brittle steel, which is nice and ductile at high temperature, at room temperature. Cool it down, and just breaks like a piece of glass. Okay. So then there was a commission set up by the government. They did a lot of testing, and then, of course, ductile to brittle transition. This whole thing came about. And now in engineering specs, like ESCO Corporation will say, we want this kind of foot-pound toughness at minus 40 degrees, something like that. And a piece of trivia that I want to share with you, minus 40 degrees, you don't have to specify whether it is C or F, right? Because at minus 40 degrees centigrade and degrees Fahrenheit are the same. Minus 40 degrees. Now, last couple of these, and then we'll do some show and tell. These are design guidelines, which I basically stole from the book. It says, I'm sure you cannot read this, but I'll read it for you. Design of welded parts and structures must be done to perform the required function with the least amount of material and the minimum amount of labor. There's a tendency for people to think more is always better. For example, weld metal, put a lot more. In fact, you should be thinking about put a lot less. Okay? Because it turns out that the weld metal is like 10 times as expensive as base metal. You put all the thing factors in there. The most economical solution to a design requirement will be accomplished if the designer takes into account these 10 points. 10 points. The total service requirements. What does this mean? It means a lot. The very first thing it means is types of loadings. What kind of loading are you going to see? Is it impact? Is it static? Is it dynamic? Stuff like that. Allowable working stresses. What kind of stresses are we allowed? Okay. What kind of stress concentration factors? Mechanical and physical properties of materials. Hopefully you have your material characterized. You know exactly what the mechanical properties are. Number 5, capabilities of the welding processes and properties of the weld deposit. Of course, that all depends on you, because you are the ones who are doing it. Joint types and weld types. Yes, you can go with this type of joint or this type of weld versus that type of joint or that type of weld, and there will be a difference. Okay, certainly there will be a difference. Basic properties if you go and design deeper. Fabrication methods available. Yes, there are more than one way to skin a cat. This is fabrication methods available. Do you have to do weld? You don't have to. No. Cost of welding with different processes. Of course, cost is always the overriding factor. Clear communication of the design to fabricator. This is probably the most important. The most important, clear communication. Right, Neil? I've heard stories like, you all know from welding background, that sometimes you preheat things before welding. So the welding specs are saying, well, preheat to 350 degrees and then weld. And the welder preheats it to 350 degrees, then it goes out to lunch, comes back, the part is already cold, and he or she welds on it. They're right. That's what it said, preheat. It didn't say that you preheat and then you keep it at that temperature while you're welding it. The communication is the main thing. Communication is really the main thing. And I think it's the job of the engineers, and welding managers and so forth to make sure that everybody understands. Okay, last but not the least, qualification and inspection techniques. Of course, that's where people like Neil come in.
I will make one comment, Khalid.
Please.
As far as welding and inspection, I try and tell everybody the first inspector of the weld is the guy who's underneath the welding hood.
Correct.
He sees more about that weld than anybody else will ever see.
Correct. I go into it a lot when I teach a welding engineering class. Things that you can see before weld, during welding, and after welding, just with your eyes. You can never do that with the most sophisticated techniques when the welding is done. Yogi Berra used to say, you can observe a lot just by watching. And you can. If you are a conscientious welder, and I'm sure 99% of the welders are conscientious workers, they want to do the best job they can. I mean, it's extremely valuable what they are doing right there. They could keep an eye. Very, very true, very true. So the bad news is design, materials, and production procedures are interrelated. Can't do anything about it. They're all interrelated. And if you've done things with experience, you really know down pat how to go about doing that. The last slide I want to show you. How many of you know the name of King Hammurabi?
King of Babylon.
King of Babylon, like Hammurabi.
Yeah.
Basically, he's attributed as establishing the first building codes.
Yes, exactly. The Code of Hammurabi. And I share that with my students because this is a fantastic code. I like it. Since I can read the hieroglyphics here, I'll translate it for you. All right, what it says is right here. 2200 BC, 4,000 years ago. If a builder builds a house for a man and does not make its construction firm, and the house collapses and causes the death of the owner of the house, that builder shall be put to death. If it causes the death of a son of the owner, they shall put to death a son of that builder. And on and on. This is actually how they did quality control. So bad builders basically got killed. Essentially, only the good builders stuck around to do their job. Again, I know that all of you are fantastic workers. You take pride in your work. You should. Because welding is not an easy job. It's a very difficult field. It's an extremely important field. It's a high-tech field. You should be proud of what you're doing. Okay. All right, so let's do some show and tell. Forget about these slides. Birthday or anniversary of this device. So it has been around for 100 years. A fantastic device. It can measure the strains very accurately. Let me pass this around. Basically, it's a grid, looks like wire. But it's not wire. It started out as wire, 1930s, 40s. But now, with the etching techniques that they use for silicon wafers, right, for your semiconductor chips, they use the same etching technique on the foil. The idea is this: if I were to stretch that wire or that foil, the resistance changes. And if you can measure that resistance change accurately, then you're straining. It's a very, very sensitive device. And I'll show you that. It's one of the slides that I was showing you, the test machine. The sample was stuck in there and it was filling. On the top it said load cell. That load cell which is telling me load, like 10,000 pounds, 5,000 pounds. Actually it's using strain gauges. Actually it's using strain gauges, the strain gauge bridge, that is being converted into load. The students look at it and say, oh yeah, load. No, we are actually using strain gauges. Load cell. So how sensitive is this guy? I can show you that. Again, let me pass this around. I'm very proud owner of this because I made these short courses. There's a strain gauge which has been mounted on a piece of aluminum here. And I have a similar one in there. And these strain gauges come in lots of different patterns. So you will see a very different pattern on this sample later on. Okay. So what I've done is connected this to the strain indicator. And remember, strain normally they use epsilon, change in length over my original length, right? And normally this thing is in micro inches. But if you are using inch, if this is micro inch, this is inch. So the way we call it is micro strain. Which simply means, when I say 10 microstrain, for example, that means 10 times 10 to the minus 6. Very small number, inches per inch. So with this device, I'm going to measure in micro inches, microstrain. Pretty much zero. The temperature also affects these things, so if it's too cold or too hot, worry about that. Okay, so that's zero now. Now, as you can see, that beam is pretty light, it's a piece of aluminum. And as I pick this thing up, I want to show you how sensitive this guy is. If I pick this up, it's actually registering about 7 microstrain because of the weight. There's no weight really, there's so little weight, but the amount of deformation, very minuscule, actually is being converted to strain. So it's registering like 7 microstrain. It turns out that strain gauges can read things even in negative pressure to some extent. So if I turn it around, this goes to -7, because now it's underneath it, it's trying to squish it. If I go back here, 7, 8 microstrain. That's how sensitive this guy is. And these strain gauges are used by the thousands. Companies like Freightliner Corporation, Daimler, right, and Boeing, they use thousands of these strain gauges on fuselages and so forth. And of course, they're not reading them one by one. 3 years later, they got the scanners which can do 500 channels at the same time. We have some which can go 10 channels. 500 gauges are being scanned as you're loading this. Literally used by the thousands of these things. Okay, so strain gauges. That's one way of measuring strain. Now this was applied load. I picked up, and because of picking it up, cantilever being kind of deformed, I was able to measure strain. On this, which I'll show you when you get done, I've got strain gauges. This is a huge weld. Neil doesn't know what kind of welding that is, right?
I can't see that through the table.
I'm just kidding. I mean, he has done this so many times. This is an electroslag weld, where the minimum thickness is like 2 inches and the maximum, they've done like 36-inch thick welds, 10-inch, 8-inch, no problem. And some of my students did some analysis on this with what they call rosette strain gauges. So there are 3 gauges to 1. Here, and so forth. I'll show it to you after. Strain gauge is a wonderful thing to measure strains very accurately. Okay? Applied stresses as well as residual stresses. You can do that. Now, I have another technique which is even more interesting. That's called photoelasticity. Photo from light, elasticity, of course, from elasticity. And what you do in photoelasticity, which is also around, has been around for 75, 80 years, is actually use polarized light. And if you don't know what polarized light is, this light is vibration, which is at random. If I pass it through the polarizer, then basically lets only one wave through, which is parallel to its polarizing axis. Right? It turns out that these 2 pieces of plastic have their polarizing axes at 90 degrees, which means if I put like that, then you can't see me because I have blocked. So one is going like this, the other one is going like this, but I have blocked. So this will be called a dark field arrangement, essentially. Okay. I'm trying to show you this. This is not very exciting. It's not very exciting, but when I put the 2 together, now that's a dark field arrangement, basically. And you use dark field arrangement as well as bright field arrangement at 90 degrees for different reasons. That's detail. But I want to show you the teaching type. This will be called a polariscope because you got 2 polarizers in parallel. The polariscope, teaching type polariscope. And let me show you this part first. So for example, you're designing you're designing a bracket for some kind of load. And this bracket needs to have a couple of holes. They're exactly the same diameter hole. But the location is important. This is next to the edge. This is in the middle of the body. It's important. Same diameter. Now, this is a special plastic which has this wonderful property called pi refringence, which means when I put load on it, it shows me stress with color fringes, okay, basically, polarized light. Okay, so I have this poor man's polariscope, 2 pieces of, okay, like that, not very exciting. I put it like that, that's my dark field. Okay, so I put it in there, and you don't see anything, but I'm going to start loading it with my fingers. I'll squish the 2 ends together and see what happens. All right. So not only you see colors, color fringes, and that's a very quantifiable technique. In fact, those colors mean stress levels. So blue will be, yellow will be something, green will be something, blue. And I bet the computer modeling people, solid modeling people, took the cue from here, because their color scheme is the same. High stress means red, okay, low stress means blue and stuff. So not only you can see pretty colors, but you can do very quantitative analysis. Okay? So first of all, you see fringes, and you see fringes all over, but which hole do you think might be center of trouble? Where the fringes start first? One next to the edge, right? Didn't we say that all these holes will create stress concentration factor? And you're right, they will. But it also depends on where they are, right? So the location is important. In this case, the edge, hole next to the edge, starts giving you fringes first. And then later on the other guy has to get. Now this was applied stress, essentially, right? We can actually look at residual stresses too. This photoelasticity technique. Let's do that. If you have any questions, please holler.
Does the different type of light spectrum make a difference on what you're doing?
Yeah, actually, this is just to show people the beauty of it. Real work in photoelasticity is done with monochromatic light, one color, because you want to see these things in black and white. This is just to, I love cakes. I don't know why, but I love cakes. We'll have 4th and 5th graders coming here every summer, and I am another faculty member meeting all these things. So this is basically to show them, they get excited. All right, so same thing here, polariscope. If I turn it to 90 degrees, bright field arrangement, I go to dark field arrangement. Now, these 2 samples that I have, this is a disc sample which was same kind of plastic. It was loaded in compression. It was squished this way, and then while loading, heated and cured under load, which means it has a locked in pattern of stress in it. This is a ring. As you can probably see, this diameter is shorter than that. It was squished this way and then cured in glue. Both of them have a pattern of residual stress locked in them. And all I have to do is just throw it in there, and voila, you can see that pattern of stress in there. Again, as I said, it's a pretty quantifiable technique. You can actually measure things and calculate things. That's how they did design optimization when they didn't have all these computers and things. This one is even prettier. Okay. All those color fringes. That's better.
So the different color spectrum is of a different tension, pressure? or
Yes,
what?
yes, exactly.
Okay.
Yeah, exactly. Different stress levels, basically. You can actually, you don't have to know anything about the technique or mathematics behind it or anything like that. It's a very visual technique for even quality control. Now you all know plastic cutlery is made by injection molding, right? You melt plastic and you push it into a mold. And because of that, it has residual stresses in it. All I have to do is just put it in there. Yeah, you see some colors in there. In fact, my glasses, which are not glass, they're plastic, right? I can put it in there, and because they were put into that frame, they show some color or residual stress. In fact, I can't see it now. I need another pair of glasses. But it's a very nice quantifiable technique. Again, you might say, well,
Now, does that gauge only work for transparent and translucent materials?
say it again.
I said, does that gauge only work for transparent and translucent materials?
Very good question. This is so-called transmission mode, right? The light is going through. You might say, well, I can't make a model of Boeing 747, stick it into a kaleidoscope. No, you can't. Same technique, interestingly, works in reflection mode. But this is the polarizer as well as the analyzer. Now let me show you. If you're really observant, you can tell that this beam is not straight. It used to be straight. And some of my students got a little too carried away in loading it when they put strain gauges and photoelastic coating and whatnot. So they got a little carried away and they loaded it beyond the yield point. I said, okay, now let's go ahead and really load it. This has been around for, I don't know, 25 years. And on this, what we have done, of course, there are strain gauges. We have taken the wires out, the number of strain gauges found it here. We've also put photoelastic coatings. You can buy these coatings from the same vendor that sells you strain gauges and photoelastic stuff. So these coatings are there. And because of this loading, there's pattern or residual stress in there. And all I have to do is just hold this there. And voila. I don't know if you can see it from here. But there's a pattern of residual stress in it. It's logged in there. 30 years. Stress concentration we talked about, right? Holes. There's a hole here. I hold it there. Well, in fact, this is exactly the butterfly pattern that you will get in your computer model if you put it in there. You get this kind of thing. It's a very visual and very powerful technique. That's the end of my spiel. If you want to come around closer to this guy, I'll show you how you do it with strain gauges, residual stress analysis with strain gauges. You can take it closer to it. I'm done. Thank you.
Thank you.
Could you use that type of material for laying it over welds to see the stresses? That's a pretty simple way compared to how
Right,
we
not
do
only
it.
that, but you know something? This material, I'm hoping that it's still selling it. You know, with the computer solid modeling, everything is gone by the wayside, unfortunately. I told you the sad story of my student getting 2 billion PSI without even thinking about it. I'm sure they're still selling it, but you can buy this material in sheet form, the flat surfaces, and you can buy it in a form where you actually cast it and it's still kind of flimsy and you can actually
Right. Well, I was thinking of just for the education, because I used to teach weldments, welding and stuff like that.
That's probably.
Try and get in their mind a lot of times by putting too much of a welding and overstressing it,
That'd be my
and
mistake.
things like that.
So one will have to think through the details how you do it, but it is possible to actually make it.
Yeah, I'm sure.
That's how they stress their design work 50 years ago, the real stuff.
Well, I was up in Boeing, and they were actually using something like that, to look at wings, check the different spots, and stuff like that. And I thought, that's really neat. I gotta watch a little bit of it. And it was fascinating what they can do. But they were doing it on an old, actually old wings, they ring with the planes in, and check them there and stuff like that.
Yeah, as I said, the aerospace industry was always ahead of everybody else. Yeah, they were doing that.
Yeah, but the problem is, nobody else can do stuff.
Well, nobody else has the money.
Well, actually, they do, they just.
They're bad thinking. They're bad thinking.
Well, no, it's actually right in some aspects, because right now, like, I was just talking to him, he was talking about China making all the piping and stuff like this for all their agencies and stuff like that. And yeah, they have no
Oh,
regulations.
yeah, I see.
Their standards are not ours, so they get away with all this stuff.
So I heard now that overall we do that in the real world.
I have no idea.
But it's pretty sure.
I worked for Westinghouse when we were building a nuclear plant there going into South Carolina and Johanna. When they started building the four here, they built four in China. At that time, I didn't work for Westinghouse, I actually worked for a vendor. And I did several projects. And what was funny is, even for the plants being built in China, the specs literally said, no Chinese material.
Well, yeah,
Not so much.
No Chinese and no Indian material.
From the executive.
Well, when I went to Boeing, they had put in thousands of
Engine's actually supposed to be
meters
consumed.
feet, whatever it is, pipe with 90s. Kept blowing out the 90s, all Chinese. They had to go back in, that's one reason I went up. And had them all out, start all over again. But yeah.
we're all guarded. Our QA guys all over China to make sure that they were actually following the procedures. Yeah, they had to be on site.
The problem with Chinese material is you can get really good Chinese material that meets all the specs and ASTM stuff. But then you also get what we consider, in the nuclear world, we call suspect counterfeit fraudulent items, where they'll build a valve, and like, you know, they'll build a valve and stand with Bell, right? Unless you know that Bell doesn't have a factory in China, you would not know that's not a Bell valve. And we have to work on, look for, you know, just different markets, like, okay, so
Let's say,
say the company only marks 150 pound valves, and certain marks 300 pound valves, different marks like that. So you see that triangle mark on 300 pound valve, you're like, no, that's only 150 that a triangle, the 300 is supposed to have a square. We have to do it for that. That part of Dave's job, while they're working, we can check the materials, make sure we have no counterfeit.